want to end this section by showing you that the square root of 2 cannot be written as a fraction. Now I have this written up in my book, but I want to talk you through it, and I'll give you an extra little story as a bonus. This problem has quite some historical importance. In ancient times, around 500 BC, Pythagoras, which many of you will recognize his name. He's the guy from whom the Pythagorean theorem is named for. Pythagoras did not come up with the Pythagorean theorem. That predated him by at least 1,000 years, but his name is attached to it. Pythagoras traveled the world around 500 BC, came back to Greece, and wanted to establish a school or a movement. And he created the Pythagorean school. Ultimately had quite a cult following. Hundreds of people followed it for a while. Pythagoras was actually the person who coined the term philosopher. And so as a philosopher, philosophers are interested in how nature works, how to explain things. And Pythagoras' idea is that nature is rational. By rational, he literally meant it could be represented somehow with rational numbers, with fractions of integers. And so the Pythagoreans assigned numbers to different things. You know, the sun, the moon, the earth all had numbers, and combinations of things were rational. They could be expressed as fractions. To our modern thinking, it's kind of crazy, but back then they didn't have too much to go on, so I could hardly fault them for reaching for some kind of explanation of life. One thing, the lasting contribution of the Pythagoreans is our musical system, musical notes. And so it was Pythagoras who one day walking by a blacksmith shop heard the guys inside banging on anvils with hammers, and occasionally when they struck two anvils at the same time it sounded very nice. Other times it was just a cacophony. And so Pythagoras began exploring the nature of sound, and by using strings, tight strings that could be plucked, he was explored, well, what's the difference in sound between the longer strings and shorter strings, and when do they sound well together, when do they not mesh. Through those experiments, Pythagoras pretty much came up with the musical notes that we use in music, and so all that dates to him. And originally the tunings of these notes were based upon rational numbers, simple ratios. So if you're a musician and the octave, say a note C, and the note an octave above it, which is also C, being an octave apart, this higher note vibrates twice as fast as the bottom note. But if you look at the interval from C to G, which is called a perfect fifth, the G vibrates 3/2 or 1.5 times as fast as the C below it. And so in terms of string length, if you take this string and cut it by 2/3, you create the note going from C to G, or this perfect fifth interval. All right, well, there's a lot to say there, and I'll leave that alone. But musical tuning had its roots in the Pythagoreans, in the Pythagorean school. All right, well, to get on with it, their philosophy was based upon rationality. Nature was rational. Literally everything could be expressed in terms of ratios. Well, they ran into a problem. Someone noticed that if you had a perfect square, and suppose this square was 1 unit on a side, if you connect the opposite corners, then using the Pythagorean theorem, we find that this length, the diagonal length, is what we call the square root of 2. And someone noticed that it was impossible to write the square root of 2 as a fraction. So history doesn't record who first saw this or noticed it, but as the story goes, it kind of ruined their party of the Pythagorean school, and so they decided to make this a sort of a deep, dark secret. And they towed this poor guy out to sea and drowned him. And that was the fate for anybody who revealed the secret that not all nature is rational. So people finally got past that and dealt with reality. But now I come to the main event here. I want to show you why that cannot be written as a fraction. And this proof is a classic example of early great logical thought. And so I think it's important to try to understand it. I'm an educator, and so this is why I talk about things like this. And so I think you'll gain something from trying to follow this proof. It's not difficult. You just have to concentrate a little bit. All right, so here's how we're going to do. How can we prove that the square root of 2 can never be written as a ratio of integers, as a rational number? Well, what makes this proof so classic is that to prove it, we commonly take a backdoor route. We say, okay, well, suppose we say that it is a rational number. All right, so suppose that we could write the square root of 2 as a ratio of integers. A and B are both whole numbers, we'll say. And what we're going to do is prove that this is impossible. We're going to use the logical method of reductio ad absurdum. It's Latin for reduced to an absurdity. We're going to show that this is impossible. And so if that's impossible, then we cannot write the square root of 2 as a rational number. It must be irrational. All right, so the only other stipulation I want to agree to is that if we say, all right, well, suppose it could be written as a rational, I also want us to agree that it's been reduced, a reduced fraction. So we can reduce all fractions. So I don't think anybody's going to quarrel with that. Any fraction can be reduced to its simplest form. It turns out that's a very important assumption here, to assume that we've already reduced this fraction. All right. Now I'm going to square both sides of this equation. And what is the square of the square root of 2? Well, by definition, it is 2. So the left side becomes 2. The right side becomes a squared over b squared. And then one more thing. I want to clear the fractions, so I'm going to multiply everything by b squared. So on the left, I have 2b squared. And on the right, the b squareds cancel. It equals to a squared. So this is the important equation I'm going to work from to show that, we're literally going to show that there are no integers that fit into that equation. None. And so how do we do that? Well, here's the first thing we can do. We can eliminate the possibility that a is an odd number. And so a is not odd. And why is that? And remember, odd numbers are numbers that are not divisible by 2. 1, 3, 5, 7, 9. Those are odd numbers, for example. And so if a was an odd number, then a squared would also be odd. So if a was odd, the right side would be an odd number squared, which is odd. But what about the left side? No matter what b is, 2 times it will produce an even integer. So if b is an integer, you square it, it comes out even or odd, doesn't matter. But when I multiply it by 2, 2 times b squared becomes an even integer. And so if we assume that a was an odd number, then I'd have the spectacle that I have an even number equal to an odd number. And those two sets are mutually exclusive. Even numbers are numbers like 2, 4, 6, 8. So we can dismiss the possibility that a is odd. It's not odd. So therefore a is an even number. A is even. Okay. Well, what now? Well, what if b was an odd number? Suppose that b is an odd number. Okay. and we'll just, I'll put a question mark because we haven't shown that's true, can be possible. If b was an odd number, then I have 2 times an odd number squared equals to an even number squared. Remember that a is an even number. Well, an odd number squared is odd, and so this ends up being 2 times an odd number. All right, now it's a different odd number because I squared it, but you know, odd squared is still an odd. So 2 times an odd number is equal to an even number, which is squared. All right, now they're both sides are even because 2 times this number is even. Certainly an even squared is even, but why is that impossible? Well, when you square an even number, you get a number that is divisible by 4. So this side is divisible by 4. For example, 2 squared is 4. 4 squared is 16. 6 squared is 36. 8 squared is 64. 100 squared is, 10 squared is 100. And if you go down the list, every time you square an even number, you get a number that can be divided by 4. Always. So the right side is always divisible by 4. But when I multiply 2 times an odd number, I don't get a number that's divisible by 4. It's only divisible by 2. For example, 2 times 1 is 2. 2 times 3 is 6. 2 times 5 is 10. 2 times 7 is 14. If you work down that list, 2 times any odd number gives you a number that can never be divided by 4. So the left side is not divisible by 4. Now that's not possible, is it? Because I have whatever is on the left side is not divisible by 4, but what's on the right side is divisible by 4. That's clearly impossible, isn't it? So b is not an odd number. B must be an even number also. So we've exhausted the possibility that a was odd. That's not true. A is even. We've exhausted the possibility that b could be an odd number. That's not true either. So b must be even. B is even. All right, so far, well, I only have one possibility left. A and b are both even numbers. Now, where's the problem with that? Do you see the problem with that? Remember this statement here. We have a reduced fraction. If you had an even number over an even number, it's an unreduced fraction. For example, 18 over 30. That's a ratio of 2 even numbers. It's not a reduced fraction. Any one you come up with, even number divided by an even number, can be reduced because you can divide both top and bottom by 2. And so this possibility contradicts the fact that I have a reduced fraction. So we have eliminated all possibilities for a and b. Neither one can be even, neither one can be odd in any combination you think of. And integers are either even or odd, and so there are no other possibilities. So what we've done is we've reduced this problem to an absurdity. There is no solution to this equation. Without a solution, then there is no solution to the square root of 2 is a over b. So therefore, we have contradicted this assumption. We've reduced things to an absurdity and shown that the square root of 2 cannot be represented as a fraction. So I hope you found it interesting. I first saw this in 9th grade. I didn't understand a bit of it. And but as adults, if you concentrate on it, I think you'll gain something kind of remarkable from this theorem. But this theorem can be extended. By the way, I mentioned in an earlier video that when you find the root of an integer, any root of an integer, if that root is not an integer itself, then the root must be an irrational number. It cannot be written as a fraction. As such, it has no irrational numbers. It can also be shown that when you have an irrational number, there is no pattern to the decimal form. It goes on forever, and there's no repetition that's continuous. So there you go. There's an irrational number and why it is.